Now the topic that is variation of pressure with depth. ફ્લુઇડમાં જેમ આપણે નીચે જઈએ એમ પ્રેશર ઇન્ક્રીઝ થતું જાય. તો આ વેરિએશન ઇન પ્રેશર ડેપ્થ સાથે કેવી રીતે થાય છે that we have to calculate. Now see, consider the fluid in a large container as shown in this figure. Now at the surface of the fluid, the pressure that is atmospheric pressure, because the surface of the fluid that is in direct contact with the atmosphere. So pressure exerted on that particular surface, that is atmospheric pressure, and say that is PA. Okay. Now suppose here we want to calculate the variation in pressure with the depth in this fluid. Then for that, first of all, consider one cylindrical fluid element as shown in this figure, for which the cross-sectional area of the cylinder, that is A, and upper surface of this cylinder is suppose at point 1, and the other cross-sectional end of it, that is suppose at point 2. And now suppose the height of the cylinder, that is h. So here suppose at the upper surface consider the pressure, that is P1, and at lower surface consider the pressure, that is P2. Now at upper surface, the force due to pressure P1, that is F1, which is in downward direction, and at lower surface here, force due to pressure P2, that is F2, that will be vertically upward. Obviously, because your fluid element, this one, cylindrical one, is stationary. Okay. તો આ અપર સરફેસની ઉપરનું લિક્વિડ જે પ્રેશર એક્સર્ટ કરે છે એના લીધે અપર સરફેસ ઉપર ઓબ્વિયસલી ડાઉનવર્ડ ફોર્સ લાગે, પણ એની અંડર ઇફેક્ટ તમારું જે લિક્વિડ એલિમેન્ટ છે એ ડાઉનવર્ડ મૂવ થતું નથી. એનો મતલબ એ થયો કે ડેફિનેટલી લોઅર સરફેસ ઉપર જે ફોર્સ લાગે છે એ ડાઉનવર્ડ ફોર્સીસને બેલેન્સ કરે છે. હવે અહીંયા ડાઉનવર્ડ ફોર્સ ઓનલી F1 નથી, બીજો પણ એક ફોર્સ છે. કયો? Now see, at upper surface force is F1, and another force, that is the weight of this element. કારણ કે આપણે આ જે સિલિન્ડ્રિકલ એલિમેન્ટ કન્સિડર કર્યો, તો આ જે સિલિન્ડ્રિકલ લિક્વિડ પાર્ટ છે એનું પોતાનું કંઈક માસ છે. એ માસ સપોઝ m હોય તો એનું વેઇટ mg એ ડાઉનવર્ડ હોય. It implies that here your element that is in equilibrium and net downward force, that is F1 plus mg, and upward force, that is F2. So we can say these forces are perfectly balanced because your element is in equilibrium. So we can write F1 plus mg, that is equal to F2. So F2 minus F1, that is mg, we can write. Now as per definition, pressure P1, that is F1 upon A. So F1, that is P1 into A, and F2, that is P2 into A. So F2, that is P2A, F1, that is P1A. Substitute these values here. So resultantly we can write P2A minus P1A, that is equal to mg. Take A common. So P2 minus P1, that is equal to A, and that is equal to mg. Now mass of this cylindrical element, that is m, but mass, that is density into volume. Suppose density of the fluid, that is rho, then volume of this element is how much? તો એલિમેન્ટ તો આપણો સિલિન્ડ્રિકલ છે, તો સિલિન્ડર માટે વોલ્યુમ, that is cross sectional area into height of the cylinder, so that is A into H. Replace mass m by rho Ah. So we can write P2 minus P1 into A, that is equal to rho into A into H. This G as it is. So A cancelled from both the side. Resultantly, we will get therefore P2 minus P1, that is H rho G. Now, suppose here we take this point 1 at the surface and point 2, that is arbitrarily at depth H. Then we can write at point 2, suppose the pressure is P, then P2 is now P. Point 1 is at the surface, so the pressure at the surface is PA, and that is equal to H rho G. So here we can observe this thing. The liquid column of height H exert the pressure in downward direction, that is H rho G. Clear? So with depth H, the pressure changes as per H rho G, and this P minus PA, that is called gauge pressure. That is called gauge pressure. If we take PA on right hand side, then we will get the absolute pressure at depth H. So that is P equal to PA plus H rho G. That is the absolute pressure in the fluid at depth H. So in this way, with depth, the pressure of the fluid changes. Or in other words, we can say any fluid column with height equal to H exert the pressure in downward direction, that is H rho G. Clear to all of you? The equation which we derived for the variation in pressure with depth, or in other words, we can say we derived the equation for the pressure exerted by the liquid column of height H. So in that, only the height is important for the liquid. The shape of the container and the cross-sectional area, anything is not appearing in the final equation. And therefore, this particular result, that is termed as hydrostatic paradox. And due to this particular hydrostatic paradox, you can observe one very important thing. See here, the meaning of hydrostatic paradox means the shape and the size, the area of the cross section of the container is not important thing. The important thing, that is just the height of the liquid column for the pressure. See, suppose as shown in this figure, we take 3 vessels, 1, 2 and 3. અથવા તો આપણે એવું કહેવાય કે 3 containers આવા, which are with different cross-sectional areas as well as different shapes. અને આ બધા જ container ત્રણે ત્રણ અહીંયા નીચેથી એકબીજા સાથે connected છે. Now suppose we fill the water in any one container. ધારો કે આ જે પહેલી ટ્યુબ છે એની અંદર તમે પાણી રેડો, right? And suppose you observe the water level when it becomes steady, then you can observe this thing in all the 3 container. The water level will be the same one, which suggests this thing at the same level the pressure is same one. Clear? અને હવે જો આ કન્ટેનર માટે height, આ કન્ટેનર માટે height, આ કન્ટેનર માટે height of the liquid column સેમ છે, એટલે ત્રણે ત્રણ કન્ટેનર માટે પ્રેશર સેમ થયું, એટલે જ હાઈટ સેમ આવી ત્રણેયમાં. and this is called hydrostatic paradox. અહીંયા જો આનો ક્રોસ સેક્શનલ એરિયા અલગ છે, આનો અલગ છે, આનો અલગ છે, ઇવન શેપ પણ બધાના અલગ છે તોય. ક્લિયર? મીનિંગ ઓફ હાઇડ્રોસ્ટેટિક પેરેડોક્સ ખ્યાલ આવી ગયો?
Yes, sir.